Good morning, dear students. Namaste. We are in the three-dimensional geometry, that is planes. In the previous video, I taught the definition of plane and the first theorem. That is the first degree equation in x, y and z. That is ax plus by plus cz plus d is equal to 0. That is the first degree equation in x, y, z, three variables. That represents always a plane. Actually, the definition of plane is not there. The mathematicians decided that there are three fundamental concepts, that is point, straight line and plane. Already we discussed it in the previous video. Okay, now we are going to discuss about the normal form of plane. First is a general equation, that is ax plus by plus this is ax plus by plus cz plus d is equal to 0, or otherwise you mention it is capital letters, because already the next third, fourth theorems A, B, C will come small letters. So we mentioned this is capital letters. Ax plus by plus cz plus d is equal to 0 is a first degree equation. This is a first degree equation of plane. It is already we discussed. Okay, now the first degree equation of in x, y, z variables always represents a plane. Right? Now I am going to solve the second theorem, that is normal form of plane. This is the second theorem. You see, the first year about the straight lines in the two-dimensional geometry. There are general equation is there, 2-point form is there, intercept form, slope intercept form, normal form. Just like a 6 formations we discussed in the first year, that is in the first view. That is about the straight lines in the two-dimensional geometry. But here it is a plane, three-dimensional geometry. In the three-dimensional geometry, first we discussed about the general form, that is ax plus by plus cz plus d is equal to 0. It is over. Next one is normal form of plane. You see that, observe. We are given a plane which contains a perpendicular, a normal from origin to the plane. Origin to the plane. ON is a normal to the this plane ABC, we assume. It is a plane. It is somewhat difficult to understand it. You see that origin, x-axis, y-axis, z-axis is there. Suppose a big a pad, you take it, a pad that touches x-axis at A, y-axis at B and z-axis at C. That is in the shape of a triangle. It is in the slope form. Okay, slantly it touches y-axis and it touches, it cuts z-axis at C, y-axis at B and x-axis at A. Like that it is there. From origin to the plane, here ABC plane is there. Try to imagine. From origin to the plane, ON you say, ON is a normal, is a perpendicular to the plane. Plane is there. From origin to the surface of plane, if a perpendicular ON is there, whose length is d units. I write here d units. You assume it is a d units. The length of normal is ON is equal to d. Okay, now? And here we take a point P also. But actually this is not there. First you assume we are given a plane that touches the axis A, B and C. Suppose ON is a normal, a length of perpendicular D units. Yes. Okay now. O is horizontal, N is the foot of the perpendicular. Here is 90 degrees. Okay now? Yeah. Along ON, if N cap is a unit vector, we assume N cap is a unit vector. ON length is 2 units, it is given in the statement of the theorem, and N cap is a unit vector. N cap is a unit vector along ON direction. Okay now? Then can you find the equation to the plane? That is the question. Once again you assume, once again you hear me clearly. A plane, it is horizontal x-axis, y-axis, z-axis. A plane, that means a pad, a surface. It is slightly, it is placed on x-axis at A, y-axis at B and z-axis at C. Okay now? From origin to the surface of the plane, ON is a normal whose length is 2 units. It is given in the statement. And N cap, we are assuming N cap is a unit vector along the ON direction. That is okay. Now, can you find the equation to the plane? Certain. To take P is any point. P is any point in the plane. Not only here. We take here, here. Everywhere is there. At any place, if you take on the surface of ABC plane, P is a point. Such that OP is R units. We assume it is a R unit. R bar, not the units, R bar. OP is R bar, a vector. We are taking a point P. P is any point in the surface of the required plane ABC. Then such that OP bar is R bar. Okay now NP bar, I want to join N and P. N is the foot of the perpendicular, foot of the normal from horizon to the plane, and P is any point. Then know that the N and P are lying on the plane itself. So NP is a vector that is perpendicular to ON. Okay now we will come to right. You see, this is a normal form of the plane. Let D is length of perpendicular drawn from origin to the required plane. Already we discussed. ON is the perpendicular to the plane. Let N cap be unit vector along ON. What I taught there, we discussed there, I am writing on the board. D is the length. N cap is D is the length of ON. N cap is unit vector along ON. Then ON bar is ON bar vector. I am taking it ON vector. That is a length into direction. D is the length ON. D is the length and N cap. Okay, Nana? ON, there ON is a length only, normal only, perpendicular from horizon to the surface of plane. But we are taking ON as a vector. Vector means magnitude as well as direction. N cap means direction. Unit vector means direction. So length, D is length, N cap is unit vector. Okay now? That is ON bar. Again let P be any point on the plane. P be any point on the plane. Now you see, observe it. Now here Pn is perpendicular to ON. No doubt. P is not only there. You take anywhere on the surface of plane. Pn is no doubt perpendicular. The surface of plane is like that. Origin is there. ON. This ON is entirely perpendicular to the surface. You see my right hand. This is surface of plane. This is origin. ON. You take any point on this surface, NP perpendicular to ON. Suppose P is there, NP is perpendicular to OL. Suppose P is there on the surface of the plane, NP is perpendicular to OL. Okay, na? Like that. So, PN is PN or NP? Who write NP? NP is perpendicular to OL. That implies, now I want to change this in vectors. NP bar is perpendicular to OL bar. You agree? Yeah. Now, two vectors are perpendicular. In dot product, in scalar product, if two vectors are perpendicular, their dot product is 0. Okay, na? 0. 0, not 0 bar, 0, simply 0. You see, A bar is perpendicular to B bar. Then A dot B is equal to 0. We know it because cos 90 is 0. So Pn bar dot of OL bar is equal to 0. What is Pn? Pn is a free vector. Any free vector expressed as a difference of position vectors of terminal and initial. We know it first. And this is OL bar as it is. Okay, now this is R bar. We are taking OP bar as a R bar. Already it is. Here we may write it as such that OP bar is equal to R bar. We are assuming R bar. OL bar is, what is OL bar? It is length D n cap. Dot length D n cap is equal to 0. Already OL is there. So R bar dot D n cap. R bar dot n cap. Okay, na? The distributive line is followed by dot product. So R bar dot D n bar, n cap, minus D to D, D square, n cap into n cap dot n cap dot n cap is equal to 0. This is R bar dot n cap minus D square n cap dot n cap, unit vector, dot product of unit vector itself is 1 universal. So R bar dot n D n cap is equal to D square. D square into what is? I am setting to this side. Okay, na? So it D square. That implies R bar dot n cap is equal to D1. Okay, na? This D and square. D square is there on both sides. Numbers, they are scalars, numbers constants. So it cancels. So R bar dot n cap is equal to D. You see there? This is normal form of plane. Okay, na? Normal form of plane. Because here D is a length of normal, so it is called as a normal form. N cap must be a unit vector along the norm. This is a normal form of equation. This theory proof also needed to know it. You learn it also. Now, so this is a second one. Now, first, observe. Equation to the plane which passes through x1, y1, z1. Say A. B. x2, y2, z2. C, x3, y3, z. Fine. Write it as a fine equation to the plane which is passing through the 3 points. A, x1, y1, z1. 3 points there. 3 points are there in the space. A, B, C. Through that 3 points, a plane no doubt will pass. From any 3 points on the space, a plane can pass. Then what is the equation of that plane? First is ax plus by. First one is ax plus by plus cz plus d is equal to 0 is general form. You name it as a general form. Okay, na? This is general form, first degree equation. X power 1, y power 1, z power 1 constant. This is a first degree equation in x, y, z represents a general form of a plane. Next one is a normal form. That is normal form is r bar dot n cap is equal to d. R bar dot n cap is equal to d. Okay, na? That is a normal form. Okay, na? Here one more thing I forgot. If r bar is suppose xi plus yj plus zk dot of n cap, say it is somewhat li plus mj plus nk is equal to d. Yes, yes. Then also we can say r bar is a general point p x comma y comma z. xi plus yj plus zk, we can turn it as into general vector. N cap is li plus mj plus nk. We are naming. N cap is unit vector. L, m, n their components. D is simply d. Then it can dot product I dot I will. So Lx plus my plus nz is equal to d. Okay, this is a vector normal form. Actually, it is a vector normal form. This is a Cartesian normal form. Both are same. Don't confuse. In vector or in a Cartesian form. Don't forget. Okay, now? Right. Now, we are going to third one. The equation of plane which is passing through 3 points. Not normal, not length of normal is not given, not x, y, z in the first degree equation. But it is a different one. The plane is passing through 3 points. A, B and C. A, B and C. You see, proof. You see, this is a plane. A is there. It is x1, y1, z1. B is there. It is x2, y2, z2. And C is there. It is x3, y3, z2. Slowly try to understand it. We are given 3 points on the plane. I am writing this as a plane. You assume it is a plane. This plane is passing through 3 points. That means